So valence electrons are very important in chemistry. So we need to understand what valence electrons are. For the main group elements, the valence electrons are those in the outermost principal energy level. Conveniently, that corresponds to the group number. So when we look at the periodic table and we use the group numbers with the letter A after them, 1, 2, 3, 4, 5, 6, 7, 8, for those main group elements, that's the number of valence electrons that the elements in those groups have. The other electrons are called core electrons because they're on the inside, like the apple core. So the number of valence electrons is one of the most important factors in how elements behave, chemically and physically. So we learned about Mendeleev's periodic law, where he arranged the elements so that elements in the same column have similar chemical properties and physical properties. Now we can understand the reason for that. Elements in the same column have the same similar properties because they have the same number of valence electrons. So group 1 has 1 valence electron, group 2 has 2, group 6 has 6, etc. So let's write an electron configuration for phosphorus and identify the valence electrons and the core electrons. So phosphorus is element number 15, so that means we've got 15 valence electrons. So here's phosphorus. I'm just going to make a note, 15 electrons. So we start putting the electrons in. They go into the lowest energy sublevels first. So the 1s is the lowest energy. We put 2 electrons in there. And then we go to the 2s, fill that one up, 2p. We get up to 3s. We can keep track of how many electrons we've got going on here. We've got 2 plus 2 is 4, plus 6 is 10. We're at 12, so that means we need 3 more electrons. And so the next highest sublevel in energy is 3p, and so we'll put 3 electrons in there. The superscripts here should add up to the number of electrons that the atom has. Any questions? So now let's identify the valence electrons and the core electrons. So the valence electrons are going to be the ones in the highest principal energy level. So if we look at these large numbers here, 1, 2, and 3, those are the principal quantum numbers. And so the valence electrons are the ones that have the highest number. So there are 2 terms here, 3s2 and 3p3. Those are both, in the 3rd energy level. So our valence electrons are these guys. I abbreviate that VE, valence electrons. How many valence electrons? 5. And what group is phosphorus in? It's in group 5, right? 5 valence electrons. And then the core electrons are everything else. So those are the core electrons. Okay, any questions about that? I gave you a preview of this last week, but now we're going to officially cover it. So the periodic table can be divided into different blocks corresponding to these sublevels S, P, D, and F. The group number corresponds to the number of valence electrons for the element, and the row number for main group elements corresponds to the highest principal quantum number for that element. So here's the periodic table showing orbital blocks. So the blue here represents S block elements, pink is P, yellow is D, and green is F. And so we can find on this periodic table the order of filling that seems a little mysterious. So the S block, an S sublevel has how many orbitals? There's 2 electrons, 1 orbital, right? So one orbital, 2 electrons. And so here we see that there are 2 columns, and that corresponds to the S block. The P block, the P sublevel has how many orbitals? 3 orbitals, right? 6 electrons, right? So when we were drawing, orbital diagrams, right? We made, there was 1s, there was 2s. Each orbital can hold 2 electrons. And then 2p, there were 3 orbitals, which would correspond to 6 electrons, right? So hydrogen and helium, and those are the little baby brothers, and so they kind of they're not always where they're supposed to be. Helium, for this purpose, should probably be over here. Those represent the 2 electrons that would fill the 1s. And then here we have 2 electrons, 2 blocks, 2 elements here representing the 2s. And after 2s, we go over here and we count 1, 2, 3, 4, 5, 6. And those would represent the electrons that are filling up this level. And so after 2p, we go to the next row. This is 3s. And there's 2. Yes?
So each block is an orbital that contains 2 electrons.
Yeah, in this orbital diagram, each square is an orbital that can hold 2 electrons.
So like when I thought it was 6, it's 3 because each one holds 2. So
Right. The 6 was correct because there are 6 electrons, but it's 3 orbitals.
Okay.
Yeah. And so in my quantum hotel analogy, the orbitals are like beds, right? And so in this first room, there's only 1 bed, and you could put 2 people in it. Okay? That's one of those things that's a little hard to get straight. So I'm glad you asked the question. So we've got 3s, and after 3s comes 3p. So we've got 3 orbitals there that could hold 6 electrons. 1, 2, 3, 4, 5, 6. That's not a coincidence that this section of the periodic table has 6 columns. What is mind-boggling to me is that Mendeleev put the elements in this order before we knew anything about quantum mechanics. Didn't even really know about electrons. But he just observed patterns, and then later the quantum mechanical model is discovered, and it fits so perfectly with the arrangement of the periodic table. So after 3s, we come over here. The period corresponds to the principal quantum number of the highest occupied level. So now we're 4. These 2 here represent filling up 4s. That is not the same order that you would think. You'd think that 3d comes next, right? But remember, there's this interaction between electrons and this splitting of sublevels, and so things get all wonky. Well, here on the periodic table, we can learn how to read that, and so we don't even have to remember what's going on. So next is 4s. After 4s is this D block. So we've done 1 and 2. The third principal level has 3 sublevels, S, P, and D. But we haven't gotten the D yet. These are the 3D electrons. So how do we remember that this is 3D and not 4D? Well, I kind of think of it as like this has this section kind of sank, because it looks like with this stair-step thing going on that it should come here, right? And you've got a slinky coming down coming down the steps, and now all of a sudden this step is a lot bigger than we expected. So these guys, it's not what I meant to do. These guys are the period number -1. So here it's period 4. This is then 3, 4 minus 1. So for these D block elements, we've got, I'll put it up here next to the D block, n minus 1. So that's 3D. Then we get back to the main group part that is not sunken, and so this is P, and it's 4P, as we go back to regular numbering. And then what would come next? Come to the end of this, we go over here to number 37, 5S. And after 5S, 4D. Okay, so I ran out of room. What to do? I'm going to go sideways. So that's 4D. Coming through here. What's next? This is 5P. And after 5P, we come around here and we've got 6S. After 6S is, this is a D, right? 5D, but then there's this gap here. And if you look at the numbers 57, 72, there's something happened there, right? Well, up here on the wall is the periodic table as it should be shown. And because of our limited space on the wall, that's how we're showing it. The reason that it's formatted this way is because it fits on a piece of paper or a screen better. We don't use these elements very much. They're unusual, they're rare, and so they're kind of just pulled out so that we can condense the rest of it. But really, as on this periodic table on the wall, after barium and lanthanum, then we get cerium. And so that would correspond to the F block. If the D block sunk down 1 level, the F block sank down 2 levels. So when you're looking for the quantum number for the F, you take the period minus 2. So this belongs right up in here. Period 6, 6 minus 2. So this is 4F. And this would be 5F. Now there is this little weirdness where we've got 1 in the D block and then we jump to the F. So we'll just kind of ignore that one and we'll go 6S and then go straight to 4F. So 4F, now we've got 7. F, and then we go back up here, we're into 5D. I'm not going to go upside down around the corner. 5D, and then what would this be? 6P. Then we've got 7S. Kind of skip that one. 5F, 6D, 7P. That make sense? Can learn to do that? Yes. Why are some of them blank? Excellent question. Because this is an old periodic table. So last year, the rest of those elements were named. Anything, well, it doesn't show on this periodic table. On this periodic table, anything that has a white chemical symbol, element symbol, those are all man-made elements. They do not exist naturally. So they are made in a lab, mostly by colliding nuclei with each other. They are unstable, they fall apart, and so they don't last very long. But they do exist and they have names. It takes a while for the scientific community to agree that, okay, let's name these guys now. So there are names for the rest of those, but they're just not on this periodic table. Excellent question. Any other questions? So the whole order of filling is right here on the periodic table. Now I think in the next one, we're looking at writing electron configurations. So before we look at that simplified periodic table, I'd like to go back to this one. And let's pick an element. Maybe let's do gold. In honor of my son's wedding, we exchanged gold rings, right? So there's gold. If we wanted to write an electron configuration for gold, we can do this by just starting at the beginning and going through the periodic table until we get to this. We can also look at the noble gas configuration, which is going to be much quicker. To do that, we're just going to find the element we're interested in. We're going to go up one row and go all the way to the end. The previous noble gas is xenon. So for gold, we would put xenon in brackets, and then we would look at what's after xenon. So over here, this is period 6, so this is 6s. So we go 6s, 1, 2. And then we've got this 1, so we're just going to kind of leave him off to the side. And we're going to do this whole section down here, which is 4f. And you can count if you forget how many are in an F. 4f, 14. And then we'll come up here and finish 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 5d9. See how that works? You can also read this last term directly off of the periodic table. This is in this D block. The D block number is 1 less than the period. So this is 5D, and then just count across. This is position 9. Now, that's not matching up with what's on the periodic table, is it? This is showing 6S1 and 5D10. We'll talk about why that happens in a little bit. Essentially what happens here is this one of these 6s electrons is going to be in this 5d orbital instead. So maybe gold wasn't a good one to choose for this example. Any questions though about the process of using the periodic table? So let's do this one. Look at these examples. So if we're going to do chlorine, we find chlorine on the periodic table. For the noble gas shorthand version, we just go to the previous row and find the noble gas there at the end. So that's neon. So by putting neon symbol in brackets, that's standing for the electron configuration of neon. And then we just have to do what comes after it. So then here, we've got 3s2. And there's no D block here, and so we'll go to 3p, and we're going 1, 2, 3, 4, 5. Yes, question?
So we only introduced the D block after 4s2 because that's
Right.
when it starts?
Yeah, it only shows up after 4s2. Because the third principal energy level is the first one that has a D block. And the reason it doesn't show up sooner is because it's actually a little higher in energy than the 4s. So in the quantum hotel, you can make up your own reason. The 3D room costs more to stay in than the 4S room. In general, as you go higher floors in the hotel, the price goes up. But for whatever reason, let's make up some things. Maybe the S rooms, in my mind, are closer to the elevator. That can be a noisy place, right? And you don't necessarily want to sleep in a noisy room. And the 3D, that room would be way at the end of the hall. It might be quieter. And so the 4S room is going to be a little cheaper than the 3D room. Or maybe it's next to the ice machine. Or maybe the 3D room has a better view. I don't know. Okay, does that help? So let's do one more with a full electron configuration. Let's maybe do strontium. So strontium is right here. So if we were going to do the full electron configuration for strontium, we're going to start up here. This is 1s, and there's 2. So we can imagine building this element by adding electrons. So 1s2, and then we've got this section, 2s2. Then we come over here, and what's that? 2p, right? And we're going to go all the way across, so 2p6. And then we come here, 3s2. And we come over here, 3p6, going all the way across that one. We come down here, 4s2. And then this one is something D10, but is it 4D10? It's 3D10, because that sank down. Then here, we're back to 4p, all the way across is 6. And then here, we're finishing that block off, 5s2. So that's an example of writing a full electron configuration from the periodic table. Any questions? Yes?
When we do the shorthand of all the gases,
Mm-hmm.
so are we only picking gases?
It has to be a noble gas when you do the shorthand, yeah. Yeah. So if we wanted to do the shorthand, noble gas shorthand for this one, the previous noble gas is krypton. And all of this business here is the electron configuration for krypton. So that would be a lot shorter. So we could also write this as the electron configuration for krypton and then 5s2. You need to understand both methods. Any questions? So let's do bismuth. So first thing is find it on the periodic table. So bismuth is here. Oops, that's not what I intended to do. Bismuth, right down there. So should we do the full one or the noble gas one? The full one. I think so, because it's just good practice. So we imagine just counting through the periodic table, through the elements before bismuth, and imagine just filling up those rooms in the quantum hotel with electrons or people. So first of all, we've got this one and this one. There's 2. That's 1s2. And then next we come through here, 2s2. And then what's next? 2p, how many? 6. And then 3s2, 3p6, 4s2, and this is where things start to get a little strange. This is 3d10, and then this is back to the regular numbering, 4p, all the way across, 1, 2, 3, 4, 5, 6. This is 5s, 2. And go through here. That is going to be 4d, 10, 5p6, oops, 6s2, running out of room again. And then there's this guy, and then it jumps down here. So we're going to label this one first. That's an F, right? It's not 6F, it's not 5F, it's 4F. So the D's are 1 less than the period number, the F's are 2 less than the period number. This comes from period 6, so it's 4F. So 4F, 14. And then we'll finish this part off. 5d10. And then we're going 1, 2, 3, 6p3. See how that works? Yeah, well, once you can see it on the periodic table, it's like, oh, well, it's just all right there. So all you have to do is just count through, okay? The trickiest thing is remembering that the D, you have to subtract 1 from the number, and the F, you have to subtract 2. So, write electron configurations for each element. I think we've been through the whole thing, the beginning part, enough times. Let's just do the noble gas ones for these. Yeah, question?
So for bismuth, one we just did, because it's 5 valence electrons, it would just be the 6s2.
Excellent question. So bismuth is in group 5, which the pattern says this should have 5 valence electrons. So what are those 5 valence electrons? Those 5 valence electrons are the ones with the highest principal number. So that's going to be the 6p3 and the 6s2. I think I have a slide coming up that emphasizes that, but that's an excellent point. So in the quantum hotel, it's regardless of price, it's how many electrons are staying on the highest floor. So this 5D room costs more than the 6S. So these are higher in energy, but that doesn't matter for valence electrons. We're looking at what electrons are in the highest principal quantum number. And so that's these 2 electrons and those 3 electrons. Excellent question. Okay, so let's look at these. Cl. We don't have a periodic table on the screen, but we've got one on the wall. So what's the noble gas right before chlorine? Neon. So we can abbreviate this by just starting off with neon and then going from there. So after neon, what are we going to have? 3s2 and then 3p5. Chlorine's in group 7, and so if we look at this, we've got 7 valence electrons. So let's do silicon. Previous noble gas, again, is neon. And after neon, we've got 3s2 and 3p2. Silicon has 4 valence electrons. It's group 4. Strontium, kind of just randomly picked that one earlier. So strontium comes after krypton, right? And then the electrons right after krypton are what? The period number is 5. 5, it's the S block, and there's 2. Let's do the full electron configuration for oxygen. What's it start with? 1s2, 2s2, and 2p4. Okay. So, any questions? So, the pattern is also lovely. Of course, there have to be exceptions, right? So with that sublevel splitting, the 4s sublevel is lower in energy than the 3D, but that energy difference is actually quite small. So the 4s does fill first, but the 3D is not much higher in energy. And so some of the transition metals, they're unpredictable in lots of ways, and so their electron configurations are also a little off sometimes. Some of the transition metals have irregular electron configurations. And what happens here is that S sublevel only fills partially or not at all, and then the D level has more electrons in it than we would expect. And the way this is determined is by experiment. So these are some examples of irregular electron configurations. So for krypton, that's not krypton, for chromium, if we look at the periodic table, we would expect its electron configuration to be argon 4s2, 3d4. But actually what we find is that it's 4s1, 3d5. You're like, why? What the heck? Well, let's think about our quantum hotel. So we've got the 4s. We've got that 4s room, and then we've got a 3D room. And we've got a total of 6 electrons in there, right? So what we expect is that this one will fill first because that one's cheaper, and then we'll put these guys in. That's what we expect to happen. But let's imagine that it only costs 50 cents a night extra to stay in this room compared to that room. So this electron who's sleeping upside down in that bed says, for just a tiny bit more, I could have my own bed over there. That's definitely worth spending a little extra, right? So this guy goes over here. Do you see the beautiful symmetry in that? Right? Now, all of those orbitals are half full. You could also imagine it's like some Groupon deal where there's this coupon that if you got these 2 rooms exactly half full, you get a discount for everybody, right? So this is actually what it does, and I just make up reasons to help me remember why.
For just transition metals?
This only happens for the transition metals.
Okay.
Yeah. And if we look at copper, copper is also in that section. We see copper, we would expect it to be 4s2, 3d9. And what it actually does is 4s1, 3d10. So let's draw electron configuration for that. Actually, I'm just going to use the same boxes there. So what we expect for copper is that, right? What actually happens is this electron moves up here, and now what we've got is we've got this sublevel completely full, and this one is half full. So there's like energy bonuses or discounts when you have levels or rooms that are half full or completely full. So that's what copper does. And we see a similar thing for molybdenum. We expect its configuration to be like chromium, 5s2,4d4, and that one electron bumps up. Things get a little stranger after that. Ruthenium and palladium also have irregular electron configurations. I only will expect you to know these two. Those are the irregular electron configurations. Well, actually, that's the expected. I meant to highlight this. This is what we want to know. We want to remember what it actually is, the experimental. So I'm going to erase this other highlight. I got lost. You should know that other irregular electron configurations exist. I do not expect you to remember what they are. But if I give you chromium or copper on an exam, which I probably will, hint, hint, you should know that those have irregular configurations and you should know what they are. Okay? Any questions?